Hello and welcome to another video from Training Made Clear on the Imperial and the Metric system. And today we will be looking at lesson number 4 about temperature. We have two systems that affect us all in different areas of our lives, as mentioned below. And of these 8 different lessons, we are going to be looking at number 4 today on temperature. If you were asked to name the scales used to measure temperature, what would your answer be? Most probably you would immediately say Celsius and Fahrenheit. And maybe that will be it for you. That would be correct, because these are the two most commonly used temperature scales used in the world today. Somebody might have remembered Kelvin, but I'm quite sure that a lot of us, or very few of us, would remember there's also Rankine and Reaumur. Therefore, in order to ensure that you are fully trained up on the Imperial and Metric systems regarding temperature, we are going to look at the historical origins of each scale. The definition of temperature is the physical quantity that measures the degree of hotness or coldness of a substance, reflecting the average kinetic energy or motion of its atoms and molecules, measured in scales like Celsius, Fahrenheit, or Kelvin, indicating the direction of the heat flow, hot to cold. If we take a look at this table here in front of us, showing the category and what the temperatures are measured in, we see that for metric, the SI units, the temperature is measured in degrees C and K. Note that K does not have a degrees C sign next to it. The imperial units are measured in degrees F and degrees R. Kelvin, Celsius, and Fahrenheit are the 3 most common temperature scales used in industry, science, and everyday. Kelvin is an absolute scale. It starts at absolute 0, and its values are not followed by degree symbols. Absolute 0 is the lowest possible temperature. 0 Kelvin is equal to minus 273.15 degrees C, or minus 459.67 degrees Fahrenheit, where atoms have minimum energy, meaning their motion and vibrations essentially stop, representing a theoretical limit where a system has the least possible internal energy and entropy. Both Fahrenheit and Celsius are relative scales. You report Fahrenheit and Celsius in temperatures using the degree symbol. If we look at the historical origins of each scale, we will now be looking at 3 of them on the metric system. The Celsius scale. The inventor was Anders Celsius from 1742 from Sweden. How was it determined? Based on 2 natural reproducible phenomena, the freezing point of water or the boiling point of water at standard atmospheric pressure. Originally, Celsius was reversed. I don't think many people know this. 0 degrees represented boiling and 100 degrees represented freezing. Later, it was inverted to the modern form that we use today. Why it fits metric? Because it's divided into 100 equal units. It ties directly to water, a universal substance, and it's compatible with the base 10 measurement philosophy. Kelvin, inventor was William Thomson Lord Kelvin, 1848. How it was determined starts at absolute 0, the theoretical point where molecular motion stops. It uses the same degree size as Celsius. It's defined today as using fundamental physical constants. And why it fits metric? Because absolute universal and independent of material properties, required for thermodynamics and physics. Official SI base unit for temperature. The Reaumur scale, the historical inventor was René Antoine Verschalt de Reaumur, 1730. How it was determined. 0 degrees R is freezing water. 80 degrees RE is boiling water, based on alcohol expansion in thermometers. Why it disappeared? It was less intuitive. 80 divisions. It was replaced by the Celsius cleaner 100 degree span. We will now look at the imperial scales, the historical origins of each scale. Fahrenheit scale. Inventor Daniel Gabriel Fahrenheit, 1724. How it was determined. 0 degrees Fahrenheit, temperature of a brine mixture, which is salt, ice, and water. 32 degrees F is the freezing point of pure water. 96 degrees F is the human body temperature, later refined to 98.6 degrees Fahrenheit. 212 degrees Fahrenheit is the boiling point of water. Why it fits imperial? As smaller degree size allows finer resolution. It's based on everyday human experience, not strict scientific symmetry. The Rankine scale, imperial absolute. The inventor was William John McCorn Rankine, 1859. How it was determined. Absolute zero as 0 degrees R. Degree size identical to Fahrenheit, essentially Rankine equals Fahrenheit plus 459.67. Why it fits imperial? Allows absolute thermodynamic calculations. Retains the Fahrenheit size degrees, used mainly in older US engineering contexts. Temperature scales comparison table. If you look at on the left-hand side scale, we are going to be looking at Celsius, Fahrenheit, Kelvin, Rankine, and Reaumur. You can see the symbol is degrees C, degrees F, K, degrees R, and degrees RE. The 0 point origin for degrees Celsius was the freezing point of water. Fahrenheit was brine. Kelvin was absolute zero. Rankine was absolute zero. Reaumur was freezing water. The upper reference point for Celsius was boiling point of water. For Fahrenheit, the human body temperature originally. For Kelvin, it's the water triple point. Rankine based on the Fahrenheit scale. Reaumur, also boiling water. Typical step sizes are shown in that column, and the system association you can see in that next column, and the last column is showing where it's used mainly. The triple point of water is the unique temperature and pressure 0.01 degrees C and 611.657 pascals, where solid ice, liquid water, and gas vapor phases coexist in perfect equilibrium, allowing water to simultaneously boil, freeze, and sublimate. It's a crucial reference point in science, used for calibrating thermometers and defining temperature scales like Kelvin, because it's a constant specific condition for water. If you look at the little diagram on the right hand side, you can see a solid, a liquid, and a gas, and the triple point is where those points all come together. There is a video on YouTube. Just type in triple point and it'll take you there. There you will see a good example of that person's experiment being shown, demonstrating the triple point. Pretty interesting. In summary, the metric systems, Celsius and Kelvin, are based on nature and physics. Imperial systems, Fahrenheit and Rankine, are based on practical and human-centered references. Kelvin is the only true absolute temperature scale. Celsius and Kelvin differ only by an offset, not degree size. Just looking at some human body temperatures, oral, the average temperatures was 37 degrees Celsius or 98.6 degrees Fahrenheit or 310.15 degrees Kelvin. If you look at these scales on the right hand side of the screen, you can see we are comparing Kelvin to degrees Celsius and degrees Fahrenheit to degrees Celsius. Just look at where the boiling point of water is. For Celsius is 100. Opposite that, you will see for Fahrenheit it's 212 and for Kelvin 373.15. If you look at the freezing point of water, for Kelvin minus 273.15, for degrees C it's at 0, and for degrees F it's 32. And absolute zero for Kelvin is 0. That would equate in degrees Celsius to minus 273, and in Fahrenheit would equate to 459. Just again, some other tables showing different points and the comparison at those different temperature scales. Ways to tell temperature: qualitative to quantitative. Physical state of matter, what you observe. Use solids, liquids, or gases. So if you see something that's frozen solid, it will be below freezing point, like ice. If you see something liquid, at moderate temperature, it would be water at room temperature. Boiling or gas, high temperature, water boiling at 100 degrees C. If you see plasma, extremely hot, that would be like lightning or the sun. Phase change indicators, what you observe: melting, boiling, and condensation. If you see ice melting, you're at 0 degrees C. Ice cubes in a glass. Water boiling, you'll be at 100 degrees C. Condensation, cooling surface, water droplets on a cold glass. You can also see by the color of objects through thermal radiation how hot it could be. So if you look at the different pictures, you can see we have infrared radiation pictures there. We have some iron bars, and one is being heated up, and it's like a yellowy, sort of almost white color. And then you can see some flames like a blue, purple sort of color. So based on what we see in there, you can see a dull red color, like the heated iron rod, could be between 500 and 700. If it's bright red, it would be between 800 and 1000. If it's orange, it would be about 1100 degrees, and if it's white, it could be 1300 degrees C, like a welding of an arc. And if you see blue, like a gas flame, you're looking at about 2000 degrees C. Here is another good table showing you the different scales. And just to show you, there at minus 40 degrees Fahrenheit and minus 40 degrees Celsius, they're at the same point there. We will look at that a bit later, but just that's a very interesting point, that there is a place where degrees C and degrees F are exactly the same. So just look at all those different temperature points and what they are in the different scales. Temperature conversion formulas. I won't go through every formula there. Just take a screenshot of the screen in front of you and just go through those different formulas there. So we have Kelvin to Celsius, Kelvin to Fahrenheit, Celsius to Fahrenheit, Celsius to Kelvin, Fahrenheit to Celsius, and Fahrenheit to Kelvin. Remember to report Celsius and Fahrenheit values in degrees. There is no degree use on the Kelvin scale. This is because Celsius and Fahrenheit are relative scales, and Kelvin is an absolute scale, so it does not use degree symbols. Absolute or thermodynamic temperature. You know Celsius and Fahrenheit are relative scales, while Kelvin is an absolute scale. But what does that actually mean? An absolute scale or thermodynamic scale comes from the third law of thermodynamics, where the 0 point is absolute zero. The Rankine scale is another example of an absolute scale. Absolute temperature is used in physics and chemistry equations to describe relationships between temperatures and other physical objects or properties, such as pressure or volume. In contrast, a relative scale has its zero relative to some other value. In the case of the Celsius scale, the zero originally was the freezing point of water. Now it is based on the defined triple point of water. The original Fahrenheit zero was the freezing point of a brine solution, salt and water. Today, the Fahrenheit scale, like the Celsius scale, is actually defined using the Kelvin scale. In essence, both Celsius and Fahrenheit are relative to Kelvin. Remember, I showed you there was a point where degrees C and degrees F are the same, and a lot of people don't know that. So if you were asked where is that point, we've now seen from that chart that it's at minus 40. So if you actually have to use these equations, the formulas, converting Celsius to Fahrenheit or Fahrenheit to Celsius, you just manipulate these formulas where you say degrees F equals degrees C, and then you can manipulate the one formula into one or the other. So there is a step 1, a step 2, and a step 3 to solve this equation. So I won't go through this, and step 4. I won't go through everything to show that. I'll just let you take a screenshot of this and you can go through the mathematics on this for yourself. So that was all I have to share with you on temperature, and I hope you've learned a lot. If you like this video, please show that you like it, subscribe, share, comment and follow, and thank you for watching.